Um, so yeah, I promised to some of you already before to very briefly introduce what all this event is about. So I try to keep this brief without too much advertisement. But basically, this is just a compiler social. So the idea is, as I said, there is not so much of an agenda. We today have a couple of talks, but in general, it's really just no topic. People interested in the compiler code generation sphere in general are around and get some beer and some pizza, and then you try to find subjects that you're interested in and talk between each other, try to socialize and try to find interesting topics to talk to. And so we, just to give some history, we do this since about a year here at ETH, monthly, bi-monthly, more or less. And it's generally like each meeting is very, very different. Today we have a lot of people apparently. We have 2 interesting talks, so that pulls a lot of people. But in general, like it might be smaller. We have very different topics. Sometimes like we have people from the electrical engineering department talking about RISC-V. We have people from Java, from EPFL coming here giving us some presentations about Scala, for example. We had people from Oracle talking about their Java VM and how to run this on LVM. So if you have any talks you think would be interesting, so you can either, as some of the students coming here demand you want to talk, then I try to organize one, or if you did something interesting you believe you want to share with the community, with people here, just let me know. Now today we have 2 talks. The first one I'm going to be introducing. So this is from Sabir. So he did here his master thesis at the systems group here, together with Ingo and Gustavo. And it's a really interesting project, how to take PySpark and run it at bare metal speed. Interestingly, we're on a compiler social, so obviously there's some compiler technology involved. Which one and how exactly that's done, Sabir will present to us. Thank you.
Yeah, thanks. So yeah, hi everybody, I'm Sabir. Yeah, thanks for introduction. So yeah, this project we are working together with Ingo. He's not here, I think. Well, maybe he'll come later. PySpark, I think most of you are familiar with Spark. And yeah, and so Spark has several front ends, and one in Python is normally called PySpark. So we are interested in data processing in Python. So there was this survey by Apache Spark in 2016, and they asked the users which features they find the most important. And we have, of course, performance, ease of programming, and also the ability to do advanced analytics. And so, yeah, this is understandable. So let's look at the performance. Here's a benchmark where they compare the Spark performance with handwritten for loops in Java. And we see straight away difference almost 10 times. And so here they used, I think, Scala frontend for Spark. And as we will see, with Python, it's even worse. So let's again look at the features. So we have performance, ease of use, and expressiveness. And now I want to look at the available tools for Python, not only Spark. So we have, we have Spark, and it's pretty easy to use. They provide a nice functional data flow interface, and it's also pretty expressive, because you can use arbitrarily Python code in your user-defined functions. So next we have SQL. It's quite performant and easy to use, but you cannot express everything as easy with SQL. Then we have C++. Obviously the performance and expressiveness, but arguably it's not the best language to use for data analytics. Then there is Pandas. It's a Python data analysis library. And if we just use its data frame API, which is very similar to SQL, then we get the performance. But again, it's not as expressive because we cannot use just any Python code. We are only allowed to use the built-in functions as with SQL. And if we move to user-defined functions, UDFs, then we lose the performance. So it looks like we can only choose 2 options. We cannot have all 3 of them. But with this project, we try to show that it's possible to have all three. And the way we solve it, we achieve the high performance with just-in-time compilation. So we compile the Python code into typed LLVM IR code, and then compile it. So the expressiveness we achieve by supporting arbitrarily Python code in the user-defined functions. And we provide the same data flow functional interface that the Spark does. So let's look at the example query and the architecture overview. So I don't know if you can read this. It's quite bright, but so here's an example how you can write a query for Python Spark. So we have, I don't have a pointer, but so what this means is just that we take the output of this operator and feed it as an input to the next one, and so on. And what is also important is that this is not computed eagerly. So until we specify an action, at the end, there is no computation performed, and and this is quite nice because we can then change this computation somehow. So what we want to do is to take this query and to compile it and executable, which we can then call with our input. And we can use the same compiled library with different input, as long as it has the same schema. So if we look at the query like this, we can recognize that it has a nice structure. We can specify it as a directed acyclic graph, because every operator has only one output, and it's directed. And some operators can have UDF functions. So the first step would be to actually translate this Python code into LLVM IR. And for this, we can use the Python library Numba. I don't know if you're familiar with this, but it's a just-in-time compilator for Python. And this can give us the LLVM IR directly, so we can feed our Python functions to it and get the LLVM IR. So next, our backend is written in C++, so we have to somehow pass this DAG to C++, and for this we serialize it into JSON and then read this from C++. Then once we are in our backend, we have the whole DAG, we have the specified user functions. Now we can try to optimize this DAG. So in this example here, the most common optimization performed by databases is predicate pushdown. So if we see that there is a filter, we always want to try to move it as close as possible to the source, like here. Because what this does is this reduces the input to this operator and also to the join, which is always good. Not always is if the predicate of the filter is much more expensive than the time that we could save like this, then we don't do it. But it's a possible optimization. So in order to be able to do this, we actually have to show that this filter does not depend on the output of these operators. And how do we do this? So normally we would not be able to do this if we don't know the semantics of this map function. If we don't understand what this map function does, then we cannot say that maybe this filter filters on the output of this operator. Maybe it uses some computation performed here. So in order to show that it does not, we first have to specify a schema. So normally in SQL you have every table has schema. In our case we don't have it, so we have to generate it ourselves. So for this we just started the input, and so the number of columns we get from the number directly, so we don't have we know that, and now we just generate random names for columns, which should be unique, obviously. And we start at the input. So here we know that there are two outputs. So we just generate columns C0 and C1, and the same for the other source. And then we can propagate this information. So if we look at the map, for example, here we see the output is just take the first element of the tuple and output it. So it's the same column, C0. And then the second output is actually a computation performed on the C1 column. So for this we generate a new column. And for example, for join, we join on the first column. So we just take the name on the left. So it's C0, and then we just copy the other two columns. And the filter just keeps the same schema because it just filters out the result rows. It does not change, it does not modify the schema. So the most obvious optimization is that we see that we're joining on this column on both sides, so probably it has the same data type. So we can rename the columns and give them the same name. Right. Now, when we have this output schema for the operator, we can start and look at the actual data dependencies that this operator have, because so we have already the data dependencies implicitly in the graph by the way that the user specified the query. So we know that this operator should be before this one and so on because of the query. But we want to show that this filter actually does not depend on the previous operators. And to do that, we actually look at which operators which columns individual operators create and which they are only reading or just outputting. So if we look at the source, let's start at the top. It generates these both columns, so they are both in its right set. Then if we look at the map, so as we said, it outputs these two columns, C0 and C2, and it only reads the column C1 here to do its computation, and so it generates a new column, so the C2 is in its right set. I will later show how it's used, so it will be more clear, but yeah, bear with me now. And the same here, and then in the join, we know join reads the key column, C0. It does not produce any new columns. And the filter here, we see that it filters, it reads only the first column, so C0 in its read set. And so how do we actually compute this read and write sets? Because all we have is LLVM IR for individual functions. So here is the Python code and the corresponding LLVM IR. So as we can see, there are two inputs, C0, C1. And then C1 is used here for the multiplication. And then C0 is used directly in the output. So the first thing that we can do is to look at the output. We can, so first we see that this variable is the output, so we look at its, where it was defined. So here, and then we can follow this chain and then see that C0 was written directly into the output. So we can add C0 into the output of this operator. Then for the second variable in the output, we see that it was computed somehow. So we can directly generate a new column and call it C2, for example. So C2 is now in the right set, and also it's part of the output. And then lastly, we look again, we go through the arguments for the function and look where they're used. And we see that C0 is only used in the output, so it's not used for any calculation. But C1 is also used here, so it is in the read set of C1. And to analyze this code, there exists a C++ library for LLVM, which we use. So then, with this information, we can now see that, okay, the filter reads only C0, and C0 was produced here and here, because it's in the right sets of these two operators. So we see that the filter only depends on these two operators. So we can safely move it here. And we also might have to change the code a little bit for the predicate, because here the filter function expected 3 arguments, but here it only receives 2. So we also have to rewrite a little bit the LLVM IR. So last step, we now have our optimized DAG, and we want to compile it into this executive. So first we generate the C++ code for the DAG separately and compile it into one object file. And then we also compile separately the UDF LLVM IR into its individual object files. And then we link everything in one shared library, which is then called with a given input. Right. So let's look at some measurements. Here some simple queries. So filter sum, map filter, map join, and map followed by reduce by key. And we compare here with pandas and NumPy library. So NumPy does not provide everything, so NumPy does not have join, but pandas does. And we see that we achieve 4 to 5 times speed up compared to pandas and NumPy. And here it's interesting because we are not using any custom Python code. These are all built-in operations into NumPy and pandas. And how we actually win that much performance is because NumPy and pandas doesn't do lazy calculations. So when we say compute map function and then a filter function and then a join, what it actually does, it calculates the map and then it calculates the filter. So it produces the whole output and then reads this output again in the next operator. So it's evaluated eagerly, and that is how they lose a lot of time. So here we actually start using Python code. Here we used the GroupBy query, and and we changed the number of groups to GroupBy. So here these are powers of 2. So the blue bars are our approach. The red one and brownish are pandas. And the difference is that with red we just use the built-in functions, built-in SQL functions. And with brown we tried to use the reduce by key operator with a custom Python function. And so what we see here is that when we double the number of groups to group by, there are double of calls to the Python code, and we see that the runtime is really dominated by executing this Python code. And we're still faster than pandas with built-in SQL. And here the example code. So if we just want to use the UDFs with pandas, then the code is quite short and easy to understand. So we group by some departments in this case, and then apply this function, so argmin on every group. And if we want to use SQL, then there are more steps in between. And here's how our code would look with our approach. It's also quite fast. So we just call, quite short, sorry. We call reduce by key and then provide the UDF. Right, so here we compare to Spark, Python, and Scala. So first interesting thing is the sum. So the sum is a completely built-in operator, so it has the same runtime in Spark, Python, and Scala. But still we are 34 times faster than Python. And then if we start using Python custom code and also Scala custom code, the difference becomes even larger. So here for reduce by key, Python Spark is really slow. It's 544 times slower than just-in-time compiled query code. Okay, to conclude, so we have these three features that we would like to have. And yeah, we have high performance as shown, and we also compared it to handwritten C++ code. So for the same query, we just written the C++ loop. Yeah, but we still have problem with larger tuple size, and there is some additional compile time, which is always under 1 second, but still there is some. And right now it only works on a single core. So we provide expressiveness with a custom Python code for the UDFs. And yeah, one problem is that we are limited by the Numba capabilities to translate Python code because it does not support everything yet, but they are improving. And yeah, ease of use, we have the same functional data flow interface as Spark provides. And in theory, we can use any front-end language because the backend is in C++, and we just have to pass in LLVM IR for the UDFs and also the description for the DAG. And as long as there exists a translator from this front-end language into LLVM IR, we could use it. I think there even exists a translator for JavaScript. This could be our next target. Yeah, we don't support named tuples yet, so it's kind of cumbersome to always calculate the index that you have to specify in the Lambda function. Right. Yeah. Thanks. That's it. Questions?
Yes. So I found it interesting that you decided to optimize on the level of LLVMIR.
Yeah.
Since Python seems like easier target to analyze and look at it.
Yeah.
Is it because of the Numba and just the fact that you want to use Numba, or is it the fact that you want to have the optimizer that can work to mark the front end?
There are several reasons. So one, we wanted to have the front end as thin as possible, so that we can move everything to the backend and then, as I said, add any front end. And second was that we didn't want to optimize, to write optimizer for Python code, for Python AST. So we could work with Python AST directly and analyze it, but the advantage of this we get from Numba, we get already optimized code, already optimized LLVMIR. So of course, it's in single static assignment form, but also all the simple optimizations are already also performed, like variable propagation and so on. So yeah, these are two reasons. Yeah.
I mean, I think in real life applications you might run on hundreds of machines, hundreds of cores. Are you sure that's not like premature optimization, that it wouldn't scale, and in real life it might not be that useful?
Yeah, that's the thing. The thing with big data is that the network becomes faster and faster, and also do the processors and the memory, of course. But as we have seen, the rate of the acceleration for the network is faster than actually for the processors. And also in big data, you normally have many weak machines which are connected with a fast network. So you have many weak machines that could really benefit from which could benefit from some CPU optimization. But yeah, it's a valid concern.
Let's see. We take care. So yeah.
Okay.
I think we're great. One more question until we get.
So we've heard about well.
Yeah.
Do you do any comparison to that?
Yeah. They do similar things and still different. Yeah. Maybe we can discuss it.
I mean.
Yeah.
Cool. So yeah, thanks again.
Yeah.